Hello and welcome. My name is Ginger Gilsdorf, and I'm a software engineer at Intel. I'm really excited to be here at the 4th annual Aerospike User Summit, and in fact, I've been at them all and hope to continue that. At Intel, our partnership with Aerospike is pretty important to us. In some ways, Aerospike software makes Intel hardware look good, and in other ways, Intel's hardware makes Aerospike look good. But either way, we really enjoy our partnership with Aerospike. So my talk today is going to be pretty technical, going over a couple different benchmarks that relate to Aerospike with Intel hardware. I'm going to go over a couple different results, one being with our 3rd generation Intel Xeon scalable processors. We've done some benchmark testing with that. And then we've also worked with a company called Principled Technologies to do some benchmark testing. I'll be sharing those results. The scaling results and the application device queue results come from them. And then again, with the 3rd gen Xeon scalable processors, I've done some 3-node cluster testing as well. So bear with me. I know it's going to be heavy in the details, but hopefully you can keep up. I wanted to start with kind of an overview of some of the new Intel hardware as it relates to Aerospike software. The Intel Xeon scalable processors, the code names that you might recognize, 2nd generation was called Cascade Lake, and that's been on the market since 2019. And then recently, about a month ago, we launched our 3rd generation scalable processors called Ice Lake. And just to show some of the highlights, the difference between the 2 generations, the 2nd gen went up to 28 cores per socket. Our 3rd gen goes all the way up to 40. We've increased the memory channels from 6 to 8, as well as increasing the speed. We have our 2nd generation of persistent memory, the 200 series, that comes out with Ice Lake. This is codenamed Barlow Pass. PCIe, we've moved from Gen 3 to Gen 4. And then just an average performance comparison between Cascade Lake and Ice Lake is you should see about 1.46x performance. That's based on a bunch of different tests, and there's plenty of information on the website below if you want to have more details. With that, like I mentioned, the Intel Optane persistent memory, or I'll refer to it as PMEM as well. The 200 series has better bandwidth than the 100 series, as well as lower power. With the 200 series, you can fit up to 4 terabytes of PMEM per socket. The PMEM DIMMs come in sizes of either 128 gigabytes, 256, or 512 gigabytes. So if you wanted to get to 4 terabytes, you would use the 512 gigabyte DIMMs. And the way that works is you have each channel has 2 slots. Up to 1 can be with persistent memory, and the other one has to be DRAM. So you can fit 4 terabytes of PMEM per socket, and then that leaves you some room for DRAM as well. We have a fairly recent SSD out on the market. It's the D7. I did testing with the 5510 series. It, in general, has better bandwidth and lower latency than some of the previous generations. And then another exciting thing on the market is our 100 gigabit Ethernet series. Did this testing with the E810 NICs. And the important thing for Aerospike customers is that this NIC comes with support for ADQ, the application device queues that I mentioned earlier, and I'll go over those a bit later. Okay, so the first benchmark I wanted to cover is a comparison of the 3rd gen scalable processor versus a 2nd gen. So it's important to note that this is actually just a single node system level comparison, and there are some differences beyond just the CPU. So the diagram on the left shows the setup that I use for this. The Aerospike Enterprise Edition version 5.5. I ran on the 2nd gen Xeon, the 8280, that had the 100 series PMEM, an older generation of SSDs, the P4510, and then the older generation NICs, the XL710 40 gigabit NICs. The comparison for the 3rd gen is a 38 core part running with the 200 series PMEM, the newer generation of SSDs I mentioned, and the 100 gigabit Ethernet network adapter. But for both cases, I have one NIC per socket. I've pinned the CPU, memory, and network to the local socket, so I have one instance of Aerospike running on each socket. That system's connected to a switch, and then I have 4 external clients also connected to that switch. The clients are running at 40 gigabit, but they each also have two sockets, or sorry, 2 NICs, one per socket. So that's the setup that I've used for this testing. The benchmark that I ran, these details here are the same whether it was Cascade Lake or Ice Lake. The data set was a little over a terabyte, 9 or so billion records, and these are fairly small records, 64 bytes each. Since it's a single system, I use just replication factor of 1. The index is about half the size of the data set, and that's just because the records are so small. The workload that I'm sharing, the results I'm sharing here was 70% reads and 30% updates. And I did 5 runs of this, and reporting, the numbers I'm reporting here are the medians. So there's 3 different numbers here, and let me explain each of those. The chart, the gray bar is our Cascade Lake, the 2nd generation of Xeon Scalable. The 2 blue bars are both 3rd generation, and I ran 2 different configurations with that. The config details are down below, but let me highlight. Moving from config 1 to config 2 is where we got that, all those system level changes I mentioned, new PMEM, new SSDs, and new network adapters. So it's not, like I said, it's not just a single CPU to CPU comparison, it's really a system level. But everything else was the same. The index in PMEM and data on SSD, and that comparison there was about 1.43x improvement using the Ice Lake with all of the adjacencies, and the raw numbers are there at the bottom as well. So that's a nice improvement there, just moving from Cascade Lake and adjacencies to Ice Lake and its adjacencies. And then highlight the differences from config 2 to 3. The only thing I did actually was move the data from SSD and put it in PMEM, since that's a relatively new feature of Aerospike that you can store both the index and the data in PMEM. I wanted to test that out. And the straight comparison from config 2 to 3 is 1.77x. So it's a very nice improvement in performance that you get from moving your data. The 2.55 number on there is slightly misleading. It's really going from the base Cascade Lake 2nd gen to the more premium version of the 3rd gen Ice Lake. But the main numbers there are 1.43 going from 1 gen to the next, and 1.77 going from data on SSD to data in PMEM. The next set of benchmarks that I'm going over were actually performed by Principled Technologies, and that's a company that we've worked with. We commissioned them to do some testing, mostly around ADQ. I'll give you a brief intro about ADQ before I go over these results. ADQ stands for the Application Device Queues, and this is a hardware-based queuing mechanism that comes, the capability to do this comes with these Intel Ethernet NICs or Ethernet adapters. And it's, like I mentioned, hardware-based queuing based on the application. So running Aerospike on a box, you can dedicate almost all of those hardware queues to Aerospike. And then this increases performance. Instead of having the network traffic kind of random and spread out, you have it really narrowly defined. And these hardware-based queues really do improve performance, and they also reduce some of the latencies and the jitter associated with networking. So what PT, or Principled Technologies, did with this is they went from a single node to 2 Aerospike servers up to 3 servers. And they compared read performance with and without ADQ. They actually did this on Cascade Lake. This is a different CPU than I used. It's a Gold 6258R. And they actually tested with both the index and data in memory. So this is why some of the results will look a little bit different. And they did use replication in this, but since it was 100% reads, the impact of those extra writes isn't evident in this test. The bar graph here shows the read performance with and without ADQ for each of those, from 1 server up to 3. And you can see that ADQ on clearly makes an impact in the performance. And then when we look at scaling, the top gray line here just shows if you were to have perfect scaling from 1 to 3 nodes, and then the purplish line, there is the ADQ results. You can see they're very, very close to that linear scaling. The ADQ off results are still impressive, but not quite as close to linear scaling. So we hope that's what you're seeing in your setups as well. I should mention this testing was completed very recently. At this time that I'm recording, the report is not complete yet, is not published, but by the time the Aerospike Summit is here, it should be published on either Principled Technologies website, or I will also try to post it at the Intel booth in case you're interested in seeing those results. Okay, going back to, let me just move that out of the way. Going back to the 3rd generation Xeon Scalable processor. This benchmark is one that I ran and actually just very recently completed. This one is actually 3 nodes with replication. The blue line there is storing the index in PMEM and the data on SSD. The orange line is simply moving the data from SSD to PMEM. So it's a pretty direct comparison. This benchmark, since I have 3 nodes and each node is running 2 instances, I technically have a cluster of 6 instances. The benchmark itself contains about a little more than 9 terabytes, or sorry, the data set contains about 9 terabytes. And this is 40 billion unique records. The replication factor is 2, so that does impact things as we move from 100% reads down to more writes. And again, I use the same methodology of having 5 runs for the data, reporting the median results. So this graph here is showing the transactions per second in millions. As I move on the left from 0% reads, so that's 100% writes, all the way up to the right, which is 100% reads. So the storing data on SSD, you can see that the performance does decline a little bit as you add more writes to the workload, which is expected. The data in PMEM results show that That impact is actually a little bit less with data in PMEM. And in fact, I went ahead and added the comparison points at 100% reads. Storing your data in PMEM will give you about 64% better performance. As you move down the line, we're at 60% performance difference, down to 38%, 20%, and 9%. So that impact, if you're storing your data in PMEM and your workload is more on the read-heavy side of things, that's where you're going to see the better performance difference. One more set of results, again, from this Principled Technologies report that is coming out. It should be published by the time the Aerospike Summit is on. This is, again, the same comparison of 1 to 3 nodes with and without ADQ. Same benchmark. This time I just wanted to highlight the predictability of read latency with ADQ. The ADQ on bars are that kind of maroonish or purplish color, and the ADQ off are the greenish. This is latencies in microseconds, so you certainly want a lower latency, and this is at the 99th percentile. So as you go from 1 server up to 3, those latencies are consistently lower with ADQ. And you can see the latencies seem to go a little bit higher as you move from 1 server to 3 with the ADQ off. And then this one here is showing the actual latency buckets, if you will. The percent of requests that come in at these different latency thresholds. So all of these requests for both sets of data, ADQ on and off, they're all coming in at greater than 40 microseconds. But as the ADQ off side goes over to the right, you can see that it very quickly drops where most of the requests are being serviced at about 240 microseconds or less. Whereas with ADQ off, it takes a lot longer to reach that kind of that tail where the requests taper off and the latencies taper off. So this is another good result showing how the Intel application device queues with these Ethernet NICs does impact the latencies and the predictability of those latencies. Okay, I know that was a lot, and configurations were slightly different for some of those tests. So I wanted to just kind of sum things up and draw some conclusions. If you decide to go with the 3rd generation of Xeon and those adjacencies I talked about, you should expect about a good 43% or so improvement over Cascade Lake. Certainly, if you're moving from an older generation like Skylake or Broadwell, something like that, your improvements will be even larger. Also, with the 3rd generation Xeon, putting data in persistent memory does give you some really good improvements on the range, about 9 to 77% improvement, depending on your replication factor and your read-write ratio. So if you have a workload that leans toward the read-heavy side of things, and you have data that is really important, you can put it in PMEM as well. The 3rd conclusion there is that Aerospike does scale very close to linearly, at least going from 1 to 3 nodes. And the best scaling results show up with the ADQ technology. And that ADQ technology improves latencies and reduces network jitter, which is really important to a lot of real-time applications or things that are important to be done very quickly. All right. Learn more, you can head over to Aerospike's website. They have a partner page with a bunch of some of our previous testing with Aerospike at Intel, and then we'll be putting up some of our current testing there as well. Intel's website has plenty of details on Optane, including Aerospike's workload solutions, but also others are up there as well. And then the application device queues, we have a ton of information there on intel.com/ADQ. I will be hanging out in the Intel booth, at least for a majority of the conference, so please feel free to stop by. Like I mentioned, the Principal Technologies report that I talked about, I should have that published, or we should have it published by then, and we'll be able to share that in the booth as well. Please feel free to stop by and ask any questions there, and thank you for coming.
Thanks, Ginger. That was a great presentation. Really appreciate the detail you went into in that one. There's a lot of questions in the chat, so I'm going to read some out to you if we've got time. And if there are any other questions from any other participants, please put them in chat whilst we have the expert here. So, Ginger, the first one comes from Albert. Have any comparisons with ADQ been done/published where Aerospike is using device storage, say a P4610 SSD, or is ADQ only viable with Optane memory storage with very high TPS per system?
Good question. I believe the only things that have been published have been with data in memory with ADQ, but actually that is on my list. I have a 3-node cluster set up, the same one that I was mentioning in the session. And I do have P4610 SSDs to try with that. So that should be coming out. I believe we'd like to publish, you know, a comprehensive view of all the testing that's been done with the Ice Lake system, the new SSDs, and ADQ.
Perfect, thank you. The next question, you said the records were 64 bytes in your benchmark test. Did you mean the stored size including overhead, or is the stored size bigger? If the size includes the overhead, why was the index half the size of the data?
Yeah, that actually might be a better question for you, but I believe since you know, I have a very simple data set and all of the records are 64 bytes, I believe that the index actually has some optimizations that reduces the size of the index. So yeah, that's why there is that disparity between the size of the, even though the index and the data are technically the same size, they show up differently. Is that correct, Tim?
Yeah, that's correct. On storage, we store parts of the index, but not the whole thing. We don't need to have a pointer to storage, for example, because it's already on storage.
Right.
Perfect. All right, the next question. Where would you choose PMEM over DC SSD Optane drives?
Sure. Okay, so for PMEM, if you're storing data in PMEM, your primary goal is going to be the highest performance, aside from what you would get if you stored your data in DRAM. We know that the latencies between DRAM and PMEM are close, but PMEM has slightly higher latencies, DRAM being around 90 nanoseconds and PMEM being in the couple hundred nanoseconds. But of course, with PMEM, you have larger capacities. So really, I kind of think of it as a premium setup. If you have some data that's incredibly important that you access it quickly, that's when I would go for the Optane PMEM. But if you want slightly higher latency, but at a lower cost, then you would go for the Optane SSDs.
And just one follow-up question on that from my side. Obviously, they're both based on the same technology, Optane. Can you explain to people why the SSD version is slightly slower, please?
Sure. So the PMEM version actually sits on the memory bus. If you open up your server, you've literally got the DRAM sitting side by side with the PMEM. So it is that much closer to the CPU, it's just that much quicker, whereas the Optane SSD is going over NVMe instead.
Perfect, thank you. Next question, can you divulge any details on larger SSD DC Optane drives coming out? 1.6 TB is currently the largest offering. I think it's actually 1.5 if I'm not mistaken.
Yeah, it's around there, and that actually I was happy to see that size. We have given that feedback to the Optane SSD team that Aerospike customers are interested in the technology but want to see bigger capacities. I don't have anything that I can officially say on that, but just know that that feedback has been given.
Perfect, thank you. So there's one observation rather than a question. Data in PMM really shines if the commit to device mode is used. We have observed this mode costs about 4x performance reduction with SSDs, but only about 20% with PMM. Do you have any comments on that you'd like to mention?
Let me make sure I'm understanding. You're saying that PMM does better than SSD in commit to device?
Correct, yeah.
And just kind of wondering why, or?
Yeah, well, maybe you could spend a minute to explain why that. So it's a 4x reduction in performance on some of the SSDs. It's a 20% reduction in performance when we use the PMM. The reason for that?
I guess there's probably several factors contributing to that. One being, of course, just the differences in latencies between the two devices. Another being the fact that the write block sizes can be much smaller for PMM. You actually do have cache line granularity. So instead of having to write in 4K blocks, you can do that in much smaller blocks if needed. I'm guessing those two are probably what contributes the most to that difference that you're seeing.
Perfect, thank you. And then I like this question. What's the best way to learn more / speed up about hardware talked about here for an absolute beginner? You know, you've gone into a lot of technical detail and not everyone has that background. How do we go?
What's the best way to start with that? Oh, yeah. Gosh, that's that's a great question. Probably tons and tons of YouTube tutorials out there. Intel's software, they have the software site, the Intel Developer Zone, has lots and lots of good details about Intel hardware, but then it can also generalize to some other hardwares. Reading, watching tutorials, I'd say that's probably the best way to get your hands dirty.
Perfect, thank you. All right, one more question. Why is it important to NUMA pin Aerospike instances when using PMM?
Right. This is something that we found to be highly effective. As you know, Aerospike offers NUMA pinning already for CPU, memory, and networking. And that really saves a lot of time in this cross-socket traffic. If you've got an Aerospike thread trying to access the index on a separate socket, that's a relatively expensive transaction there. And then when you add PMM to the mix with higher latencies than DRAM, you're just further exacerbating that difference there. So we've really found that you're going to get the best performance if you have one instance per socket and pin as much as possible, including networking, whether you're using ADQ or not. It's just purely performance, yeah.
Perfect. And we don't seem to have any more questions in chat. So this has been really helpful. Thank you for your time, Ginger. I found this very useful myself. I'm sure everyone else in the audience did. So thank you everyone for attending. And hopefully, we'll see you on other sessions in the summit.
Yeah, and join us at the Intel booth. We'll be there.
Absolutely.
All right, thank you so much.